Dear friends, welcome to this electrical engineering knowledge sharing channel, AMP Power System. We are discussing about the UPS system and under this workshop 9, and in this workshop 9 we have already completed copies of video where we have discussed about the basic requirement from the engineering point of view. And in the last video we said that we will be discussing or we will be sharing our views about the two block of the UPS system. One is a rectifier block, another is the inverter block. How this rectifier block does it work? That means what the rectifier block, what the electronics component this rectifier block contains, and how those components are work, and similarly what the components contain in the inverter block and how does it works. But these basic features, the working principle of this converter and the inverter or converter or rectifier, we have already learned in the class 12 standard as well as on the first year or second of engineering course, and most of you may be aware of this, but just to give a quick view on those so that during this engineering aspects review we can have a quick in our memory about this working principle. Keeping that thing in mind, in a very brief, we'll be discussing these two aspects in the two separate video. So today's video will be discussing about the converter, means rectifier block, how the rectifier works, what the various components does it contains, and what are the protection of the rectifiers. All these things as far as practicable we'll discuss in the rectifier block. In addition to that, we'll also discussing about the magnitude of the DC voltage we'll be receiving from the input AC voltage. That is a very important parameter which we need to calculate to decide the output voltage of the DCS rectifier. So let us discard the rectifier block first. So when we are going to discuss about the rectifier basic components and its working principle, first of all we have to discuss about how many types of rectifier are available. Now with the development of the electronics components or power electronics, we have a two type of rectifier available nowadays. One type of rectifier we call is controlled rectifier, another is a uncontrolled rectifier. But mostly uncontrolled rectifier, what we have already learned in the previous in the class 12 or first years of engineering, and controlled rectifiers maybe in the engineering stage only we have learned. So let's discuss both the options in details. So first is so if we look into the rectifier or converter, it is AC to DC converter. AC to DC converter, another name is rectifier. So this converter or rectifier, this is converting AC voltage, AC to DC. That is called, we call it normally converter, or this converter also we call it rectifier. So this rectifier, if I look into this rectifier, the rectifier we can classify into two different parts. One is called uncontrolled rectifier. Okay, uncontrolled. Another is a controlled. Why this name is so, when we'll be discussing it will be clear. This uncontrolled rectifier and the controlled rectifier, these two rectifier using different type of electronics component. Uncontrolled rectifier means uncontrolled rectifier, what it is doing, it is giving to the if this is the rectifier block. If this is the rectifier block, it has the input, it has the output. Input we are giving the AC voltage and output we are getting the DC voltage. This is the job of a rectifier or converter or any type of control or uncontrolled rectifier. Whether we are using controlled rectifier or converter or uncontrolled rectifier or converter, both the converter has a function converting AC voltage to DC voltage or AC current to DC current. That is the function of the rectifier. We have already seen the rectifier is an integral part of the UPS system. When we have discussed the UPS system, we have seen in the UPS system there are three blocks actually, or you can say fourth block, and this is the input AC voltage we are giving. It is converting to DC voltage, charging the battery, and then the battery is getting discharged through this is the inverter block, and this is a converter or rectifier block, and then we are getting the output DC, and then we have a bypass arrangement. Okay, this is the inverter system, UPS system. Out of this UPS system, today we are discussing this block, the converter or rectifier block. Okay, so when we look into the controlled or uncontrolled rectifier, how it is being classified. In case of uncontrolled rectifier, the basic components which we are using, that is the power diode. Here we are using power diode. So this is the basic component for the uncontrolled rectifier. But when we are using the controlled rectifier, we are using the silicon controlled rectifier. We call it SCR, silicon controlled rectifier. So there is a basic difference. Now I am not going in details of this diode construction, PN junction, PNP junction, all these things that we have learned. Simply the power diode, it has a two terminals. One terminal we call is the anode terminal, that is a positive terminal. Another is a cathode or negative terminal. And this is the symbol for the diode. Okay, this is the symbol of the power diode. So when we are looking the diode, it is a PN junction, the anode is the P and cathode is the N junction. So we are not going the details. So when we want to represent the power diode, this is the symbol for the power diode. It has the two terminals. One terminal is called the anode terminal, another terminal is called the cathode terminal. Okay, this is the cathode terminal. So this diode is actually, it is nothing but a switch. You can consider diode as a switch. It has a two state. One is a conducting state, another is a non-conducting state. Like our switch, suppose this is a mechanical operating switch. So we operate the switch by hand. So it has also two states. When you close the switch, that is one state, that is a closed state. And when you open the switch, then it is called open state. So this is a mechanically operated switch. The diode is nothing the same like a switch. But this switch is not operated mechanically. It is operated electrically. How it is operated? This characteristics of the diode is like that. When this anode is positive with respect to the voltage point of view, if the cathode voltage is, suppose this is the cathode voltage 0. So till the anode voltage with respect to cathode voltage is 0, we are considering in this way. And anode voltage, suppose this is 0, this is 1, 2, 3, 4. Again it is gradually decreasing. That means it is again 3, 2, 1. That means when the anode voltage is 0, there is no, the switch is open. This is a switch, this switch is open. The moment this voltage become 1 and cathode voltage is maintaining 0, then it become positive. Immediately this switch become closed. That means the switch is like this. Now it is a closed state. And when how much time it will remain closed? Till the anode is positive with respect to cathode. Cathode is 0. So till it is anode means that then it goes to anode is going 1 volt, 2 volt, 3 volt, 4 volt. That is maximum. Then again anode is, that means 0, 1, 2, 3, 4. After this time anode is positive. Then what is happening? Again it is coming back, reverse order, but still anode is positive with respect to cathode, because when it is a 3, that means at this point it is a decreasing order, but still it is above the cathode voltage. So still it is closed. When this coming over this point, suppose this is suppose it is a 0 second and this is a 6 second. So after 6 seconds it becomes 0. So after 6 seconds this switch is on. After 6 seconds anode voltage, suppose it becomes 0 or there is no voltage. And cathode is also 0. So there will be no conduction. That means the switches get open. So that means this diode is a characteristic such that it is like a switch, but the switch is operating when a switch is closed state when anode is positive with respect to cathode. But the moment anode is become same voltage as cathode or the negative voltage with respect to cathode, suppose anode is a minus to 1 volt. In that case, anode is negative. In that case, the switch is open. So when anode voltage is positive, switch is closed. When anode voltage is negative with respect to cathode, then the switch is open. So these two states we using for this purpose. So this means, that means diode, power diode or diode is nothing but a switch, but this switch is a electrically operated switch. And how the switch is getting operated? When the anode of the diode is positive with respect to cathode, anode is conducting. When anode is negative or same voltage with respect to 0, diode is not operating, diode is open. Okay, so these are the two states. So in this two state it is operating. So this is the basic way the diode works. Okay, that means we can represent the diode in another way. Suppose this is my switch. Okay, and this is a anode voltage is connected to this. When anode is positive, the switch is closed. That means When anode positive, switch state is like this. It is closed. But when anode is negative, okay, when anode is negative, this is anode negative, then the switch is open. These are the two states of the anode, of the diode. So this is the diode basic characteristics. And the other part, the other device which we are talking about, by which we can control the rectifier, that is called control SCR, control rectifier, which is achieved or by which the rectifier function is controlled, is called silicon control rectifier. The silicon control rectifier, difference between silicon control rectifier and the Pire diode, silicon control rectifier is also like a diode, but it has another features. What is that feature? It has another terminal. That terminal we call a gate terminal. So if you see the SCR block, SCR has a 3 terminal. Okay, one is a anode terminal, anode is a cathode terminal like a diode, and then we have a gate terminal. These are the 3 terminals in case of SCR, silicon control rectifier. By the name you can make it. The silicon is the name coming from the silicon is used for this, and C for control means this rectifier. This is also diode, but this diode can be controlled by another terminal, that is called gate terminal. So as this is a 3 terminal and it can be controlled, the operation is controlled by another terminal, we call it a silicon control rectifier. So silicon control rectifier, how do we represent? It is represented like a diode, but it has another terminal. This is terminal we call is gate, and this is a cathode and this is a anode. It is same like this. This is the addition to this silicon control. In case of silicon control rectifier over diode, these are the additional terminal, gate terminal, which is called the control terminal for the diode. If you say in light of diode, then we can say it is same. It is a diode, but the diode has the additional terminal which is controlled. That terminal is called gate, and this is the symbol of the SCR. Okay, so SCR is also diode, but here what is the difference? In case of power diode, diode is closed switch when diode anode is positive. Till anode is positive with respect to cathode. In case of diode, is a closed switch. The moment anode is negative or same voltage with respect to cathode, the diode is a open switch. In case of SCR, it is the same. It is also like a switch. It is a switch. We can represent this is a switch, but this switch has two functions. This control is not like a simple diode. It has a anode voltage is one of the point, anode positive, and then in addition to this, anode voltage is one of the control parameter. In addition to this, gate voltage is also another parameter. To make this switch closed, that means like a diode, if you want to close this switch, what we need? We need to, anode should be positive with respect to the cathode, like a diode. In addition to this, the gate terminal of the SCR, that should have a voltage. Certain voltage should be on the gate terminal. That means this will be positive with respect to cathode, and it should have some voltage or it should have some current. The gate terminal should have current. That means there are 2 parameters here. One parameter is anode must be positive. In addition to this, there will be gate voltage to be applied. The moment gate voltage is applied, immediately this switch become closed. Okay. Now, then once the anode become negative or same voltage, then the switch become open, whether gate voltage is present or not. Suppose gate voltage is present, but at that time, if you make the anode negative, immediately it will become as a diode. That means gate has no control. On the switch is closed, then gate has no control on the SCR. The control will come to the like a diode control. Okay. So during only the gate has a control during closing state. When you want to close the switch, then the gate has a function. But the moment switch is closed, then if you want to switch open, gate has no function. It will open how? By anode current. The anode voltage, the moment anode voltage becomes same as cathode or negative with respect to cathode, it will off, or we have to forcefully, we call it commutation. By the method of commutation also we can switch off. So these two basic difference between diode and SCR, SCR we can control for switching on, but that is one of the difference. And second point, the diode in case of SCR can be stopped conducting by method of commutation, which diode cannot. So these are the two basic difference. But otherwise, diode and SCR both are doing the same job to convert AC voltage to DC voltage. But in case of diode, we don't have any control. But in the case of SCR, we have any additional control for switching on. That is for the gate terminal. So when we are using SCR in the rectifier, we call it a control rectifier. And when we are using diode, we call it an uncontrolled rectifier. Okay. So now we will go into this rectifier using diode first. Okay. For the uncontrolled rectifier, how does it work? Now, in case of AC wave, we have seen that AC, suppose we are drawing one circle only. Okay. One circle, this is our, suppose this is 50 hertz voltage. Okay. This is our AC voltage. Now, how the rectifier, when it is converting AC voltage to DC voltage, this controlled rectifier or uncontrolled rectifier both has again two types. One is a half wave rectifier, another is a full wave rectifier. What is half wave rectifier? Half wave rectifier, this is the half of the wave. This is one complete waveform, that is a duration is 50 millisecond. This is a 10 second. This is a 10 millisecond. Okay, this is 10 millisecond. This is 10 millisecond. It is a 50 hertz supply. So this is called one half. This is called one half. So if we convert, you see, this is the zero level, and this is a positive, and this is a negative. Suppose this is the anode voltage. So when suppose cathode is maintaining zero. So till the anode voltage is positive, how much? This 10 millisecond. If this voltage applied to the anode, suppose this is my diode. Okay. This is a diode, and I am closing this diode with a resistor, okay, and then coming back. Here I am applying the AC voltage. This is AC voltage. Suppose this is positive and this is a negative. So it starts, that means initially this is negative. When I apply this voltage, suppose the diode is a negative, this 0 volt. If we consider this negative diode, this is the anode voltage of the positive of the anode voltage. Anode voltage is positive. That means this voltage is applied to the anode. So first 10 second anode voltage is positive, right? This point is positive. So first second 0, then gradually increasing 10 millisecond, it become again 0. So till that time, what will happen? This anode is this is positive and this is negative. So anode is positive means the diode will conduct, current will flow through the, suppose this is a electrical lamp. Suppose you consider in this way. So current will flow through the lamp, it will come back, right? So this lamp will glow. So this lamp will glow. So how much time it will glow? If you see first 10 millisecond. And what is the current flowing through this? If we consider, sorry, this diode has no resistance. If we consider in that way, that means when the diode is closed, switch is closed, is simply current is flowing through this. Okay. So what about the voltage over here? The same voltage will appear over here, right? So same voltage means when the voltage is, suppose this is the 1 volt, 2 volt, 3 volt, this is 4 volt. So it is increasing. So if we see the output voltage from 0 second, how? First is 1 volt, then 2 volt, 3 volt, and then 4 volt. Up to when it is 4 volt AC, here is a voltage also 4 volt. Then voltage, suppose 3 volt, it come down. So what will happen? Voltage will come down over here, right? This is, I am plotting output voltage across the load. Across the lamp, what is the voltage? Okay, here. Considering diode has no resistance. So what about the voltage over here? Same voltage will come over here. So when the voltage is 0, this voltage is 0. When voltage 1, it is output is, here is voltage 1. When 2, 3, 4, same way it is 4. When then after 4, what is happening? Here voltage become 3, right? So here also voltage become 3. This is the level of 4. Okay, it become 3. Then next it come to 2. So it will come to 2. Then it will come to 1. Then it becomes 0. So what will happening when I applying this voltage over here, across the load, what voltage I am getting? I am getting same voltage like this, right? Then after 10 millisecond, what is happening? This input voltage immediately it gets changed. Now this voltage is applying over here. So now this become negative, and then automatically this become positive. So we know now when now the diode, what is the diode condition? Now diode anode is negative, and cathode is positive. So diode is open switch. Now this switch become open. So it will not able to flow any current. So how much time it will happen until this cycle is completed? So this cycle, second part, I am not getting any output current. That means the lamp will glow only for 10 milliseconds. Next 10 milliseconds it will not glow. This is a lamp will off because the switch is open, because diode is not conducting, because anode is positive. So if I use this type of diode, only one diode, in that case what will happen? Then again, when I come to the next cycle, another 20 milliseconds, what will happen? Same way, next 10 milliseconds, this part will be reflected to the second. So output you would draw over here. So there is no voltage over here. Then again there is another voltage over here. Then again no voltage. That means every cycle, only half of the cycle is reflected to the output. Another half is not reflected. So as this rectifier is converting only half of the wave, that's why this type of rectifier circuit we call half wave rectifier circuit. Okay. So what is the problem with this half wave rectifier circuit? So if we look into the half wave rectifier input and output profile, voltage profile or current profile, how you will get? Input profile is like this. This is a input profile, right? This is our input profile. This is our input profile of the rectifier. Okay. Now, if we look into the output profile, how is it? Output profile, only half of the wave is reflected to the down, another half is not reflecting. So, if you look to the output is how? This is a, you see, output will be first half cycle is coming, then up to this, then this part I am not getting anything. This is 0. Again from here to here I am getting, that means I am getting another half cycle. Then I am not getting anything. So if you look into the half wave rectifier input output, this is our input and this is our output. This input is alternating. It is a, you see, it is positive, then it is getting changed. Here what is happening? Here the current is flowing in the same direction. Okay. In the same direction, only one half is flowing, and that current is a variable. This current is not constant. If you say DC current, it is not, it is a DC, it is a direct current, but it is not constant, it is a variable DC. DC magnitude is varying. With the time, it is going up to 4 volt, and then it becomes 0. Again, it is a start with 0, going to 4 volt, 0, like this way, it is a voltage, but it is a unified, unidirectional voltage, but the voltage is not constant. So this is the output of the half wave. So what is the problem with this? Problem is, first of all, the full, I am giving the entire energy, but half of the energy is not converting. So I have a wastage of energy. That is one point. Second point, if we analyze this voltage profile from the full wave voltage to half wave voltage, if we analyze this, we can see by Fourier analysis, if you do the Fourier analysis of this waveform, or then you can see there is a lot of harmonics is coming in this waveform. So those harmonics is also not good for the battery or for the inverter, because this DC is going to the inverter, right? So, or it is going to some loads. So this is not good for that. That's why the half wave rectifier, if it is not a very small items or a small thing, not a very critical item, we can use this. But for the critical item or big items or which is a like UPS system, we cannot use this half wave rectifier system. In that case, what we have to do? We have to use a full wave rectifier, means both the waveform should be transferred. So how can I do that? We can do this thing by using 2 diode instead of 1 diode. If I use a 2 diode, in that case, when one diode is positive, the other diode will be negative, other diode is negative, this will be positive. So there are 2 ways we can do the full wave rectifier. So the best way to get the full wave rectifier, we use a bridge rectifier. You know, we have the Wheatstone bridge. In the Wheatstone bridge, there are 4 arms. So like the same way, these 4 arms, if we put 4 diode and then 2 diode in series, then that will give a best output and best quality DC output. And that's why when we use this type of critical item, we use full wave bridge rectifier. So I am not going, we are discussing that, we will be discussing the full wave bridge rectifier. So as a full wave rectifier, instead of going to other two diodes only. In one through, we want to complete. So if we want to see that full wave bridge rectifier, how is it? So we can draw it. It is actually a Wheatstone bridge which has a 4 arms. That 4 arms we can draw. So we have a diode like this. Suppose this is one diode, and then there is another diode. These are 2 parallel branch. Then we have a diode over here, and we have a diode over here. Okay. Now this and these are our power supply points. Suppose we are applying power supply over here, and these points and this point we are connecting load. So this is our, suppose the lamp we have connected over here. Okay, this is our lamp which can glow. Okay, this is a diode 1. We can see 2, and this is a 3, and this is a 4. We can turn the diode in this way. Now what is happening here? So if you see the working principle of this, how does it work? Same way, you can draw the input output here. Suppose I am giving this input. This is my input. Okay, I am drawing 1 cycle, or I can draw 2 cycle. This is a 2 cycle I am drawing, and the output I am drawing over here. This is the input, where the input is given over here. Means this point and this point is input is given. Okay, this is the input point, voltage input point. Okay, this is the voltage input point, and this is the load connecting point. Okay, these are the point where the inverter or the lamp is connected. This is a load point. This is the output. You can say this is the input of the rectifier, and this is the output of the rectifier. This is the output terminal. You can say this is the 4th terminal. This is the output terminal. Okay, output terminal I put a red color. This is my output terminal. Now how it is working, you see here. Now when this is a positive, input is positive, means this, suppose this is again, it is 10 millisecond, 20 millisecond, 30 millisecond, 40 millisecond. We have 2 cycles. So first 10 millisecond, what is happening? This point is positive. This point is positive means this diode, this is the anode, right? This is the anode, this is positive, and this diode, this cathode is positive. So it is a positive, cathode is positive means it is an open switch. This is the open switch, but this is a closed switch, right? Up to 10 millisecond. Then this and this is a negative. This negative means, what does it mean? This means this diode, cathode, anode is negative means it is a open switch, right? And this diode, what is happening? This is negative. So anode will be positive with respect to diode. With respect, if this is a negative, it has a small resistance. So this will be higher voltage than this. So if this is negative means this terminal is negative means this terminal is positive. So anode is positive. So it is again a closed switch. So first 10 millisecond, if we see this 4 diode, what is the condition? This diodes and diode number 1 and 2 is closed. Closed condition we call it a conducting stage, and open condition we call generally non-conducting state. So first 10 millisecond, diode 1 and 2 is in conducting state. So what will happen? The moment you inject the voltage over here, so how the current will flow? Current will go through this, right? This is a positive conducting closed switch, so current will come over here. Then from here, it cannot go through this because this is open. So current will go through this load. It will go through this load. It will come to this point. After coming over here, again you see here, this diode number 4 is open. So it cannot go through this. But this diode is a closed. So it will go through this. It will come over here. Once it come over here, then it will go back to the source. So current will be flowing first 10 millisecond. Current is flowing like this way. Right? This is flowing this way. This is the current path. It's coming over here. Then it is going through this, it is coming back to the source, first 10 millisecond. After 10 millisecond, what is happening? After 10 millisecond, you see this point become negative, right? After 10 millisecond, this become negative and this become positive, right? This is a positive. When this is happening, then what is the state of the diodes? Now, if you see the diode state in this case, what is happening here? This is positive means this diode, anode is positive. So this is a closed switch, right? And what is the condition of this diode number 2? This is a positive means this cathode is positive. So anode is negative. So this is an open switch. Similarly, this diode, what is the condition? This is a negative means anode is negative, right? Anode is negative means this switch is open. What is the condition of diode 4? This is a negative, means cathode is negative, means anode is positive. So this switch again open, closed. This is a closed switch. So in the next 10 millisecond, this part, what is happening? Diode number 3 and diode number 4 are closed, and diode number 1 and diode number 2 is open. That means first 10 millisecond, those diodes which were closed, now they become open due to this change of voltage. So what will happen over here? The moment is become, so this 10 millisecond, how current is flowing? This is a positive, right? This is a, this switch and this switch are closed. So current will come over here, this, because this is the input point. Current is flowing through this, it is coming over here. Then it has a two path, this way or this way, but this will not go because this is open. So current will go through the same load, same direction. You see, previous direction was here, now this direction is same direction. Coming over here, it is reaching over here. After reaching over here, there are two paths. This is one path, this is one path. But this path is open now. So what will happen? This path is closed, so current will come from here to here. Okay? Then it will come back to the, through this, it will come back to the source. So it starts from here, it goes through this, through the load, same direction, it come back over here, then it is coming back. So in both cases, what is happening? Current, through the current is same. That means if you draw the load current, first half cycle, current is same way, it is replicated over here, this first 10 millisecond. Second 10 millisecond, diode 3 or 4 is conducting, but the load current is the same direction. So it is a replica of the same direction. So if you go then after 20 milliseconds, if you go again, it is positive and it is negative. So it will be replicated of this. So it will get this way. Then next cycle, it will go this way. That means by this arrangement, what is happening? This alternating negative part also converted to positive part. That means though the current through the load is not constant, it is a 0, 1, 2, 3, 4. Then again it is decreasing 3, 4, 1, 3, 2, 1, 0. Again it is 1, 2, 3, 4. Current is continuously flowing, though it is a variable current, but continuously it is flowing through this. So I am getting the current always through the load. I don't have any missing. That means the wastage current I am now getting back, or wastage voltage I am getting back on the output side. So automatically by using this, I have a full waveform I am getting. That means full energy conversion I am getting. So automatically my loss of energy is recovered over here. So my efficiency will be higher. That is number 1 point. Number 2 point, if you do the Fourier analysis of this half full wave rectifier, full wave this positive half full wave, we will see that ripples or the higher harmonics in the output will be very less. So my ripple content will be reduced and my efficiency also high. So that I will get this privilege over here with this. Okay. So that's why most of the critical and emergency equipment or the big items or important item, we use full wave rectifier. And this rectifier, if you see the rectifier, it is actually physically, it is a small square shaped disc, like this type of disc. Yeah. Over that there are 4 terminals are there. These 4 terminals. So you look like this. All are inbuilt within this block. That is the way this diode rectifier block is getting manufactured. So this is the full wave rectifier. Okay. So this is the half wave rectifier and that is a full wave rectifier. Now, with respect to this half wave and full wave rectifier, we have said that we need to find out another important parameter. So we always know that the inverter has a DC intermediate voltage. That is DC intermediate voltage is decided by the various parameters. How the DC voltage is being used. If the DC voltage is used only for the inverter, then there will be one type of calculation. But if the DC voltage is used for some existing load or some other DC load, then the DC voltage to be decided based on the load voltage. If the load voltage is 24 volt DC, then whatever the input voltage, I cannot change the DC voltage. I have to maintain 24 volt DC voltage. So how I will calculate the DC voltage? DC voltage we call it average voltage. So how the formula, what is the value? Input voltage should be there, by who is the DC voltage, we get the required DC voltage. For that we need to calculate the output DC voltage magnitude. Now what about the shape you are getting here? You know this waveform, DC full wave rectifier we are getting like this, right? And half wave rectifier we are getting like this. Half of the wave I am getting. Now if you see the half wave rectifier, this is a peak value, right? This is a peak value. Now, if you look the average DC value of this, how much that we know the formula VDC, or we call it V average, that is equal to V peak divided by pi. Pi means 3.1414, right? So, this is the pi value. Pi means 22/7. Now, V peak, we know the V peak, we can calculate V peak, and then we are getting pi. And if you know the this V peak again is related to VRMS, so how we can calculate VP equal to, we know VRMS is how much equal to, that is equal to, if you calculate this VP in terms of RMS, it is equal to √2 by VRMS, right? VRMS, that is divided by pi. This is a VP, because VP, that is equal to √2 1.414, right? We know this 1.414 into VRMS. That is the VP and VRMS relation. So if we replace VP by this, so we will get this is equal to pi. You will get, this is equal to, you will get approximately 0.45 upon the 0.45 VRMS. If you calculate this, okay, this is case of half wave. So in the case of half wave, the DC output will be coming in terms of VP. It will be only VP by root pi, that is equal to approximately 0.3, yeah, 0.3 VP. If this is the VP, the average value of this will be like this, only 30%, approximately 30% of the VP. And if you terms in terms of VRMS, it will be about, this is the in terms of VDC, how much it will be? It will be about 0.5, is about 50% of the VRMS value. Okay, the VRMS. This will be the average value of VDC output. Okay, in the case of half wave. Now, if you go to the full wave, then how much it will be? It will be similarly, we can calculate the full wave. In the case of full wave, what is happening? Another half we are getting, right? So it will be simply 2 times. So it will be into 2. That means that equal to 2 into 0.45 what we have get into VRMS, right? This is equal to approximately 0.09 VRMS in case of VDC. So if you want to VDC, this value will be approximately, in the case of full wave rectifier, if this is the VRMS value, suppose this is the VRMS value, so VDC will be approximately 0.9 of VRMS. That will be the calculation of this. So normally when you see 230 volt AC, right? 230 volt AC, that 230 volt actually RMS value. Okay, from that RMS, suppose if you give the 230 volt AC RMS value, then you how much output DC will get? 230 into 0.9. From that you can calculate how much DC voltage you are getting. So now if you want to, suppose I need only 120 volt DC. In that case, what will happen? If I give this 230 volt AC input to the rectifier, it will not give 120 volt. So if I want VDC 120 volt, okay, in that case, what is the AC voltage I need to put? 120 volt DC, that equal to, suppose I am getting 0.09 into 230 volt, right? VRMS. That is the VRMS equal to 120 divided by 0.9. So whatever the value it is coming approximately how much? 93, about 140 volt. That is the voltage I need to input. If I want to get 120 volt DC output, I have to give RMS value about 140 instead of 120 by 0.9. VRMS will be approximately 140 volt. But I have a output is 230 volt AC input, so I cannot use this 230 volt. What I need to do here? I need to put a transformer. What I need to do? I have to put a primary one transformer here, that is 230 volt. The secondary will be 140 volt. That 140 volt will go to the bridge rectifier. Okay, this is a bridge rectifier, then I will get the output. In that case, I will get the DC output 120 volt. Okay? So that's why when you use the rectifier, you will see in most of the rectifier there is the input transformer. The input transformer actually required to maintain to meet the DC voltage requirement. Okay, so this is the calculation for the DC voltage. So simply we can say that VDC output in terms of VRMS in case of full wave rectifier, VDC in the case of full wave rectifier equal to approximately 0.9 VRMS, and in case of half wave rectifier it is for full wave. And in case of half wave rectifier, it will be 0.45 VRMS. Okay, so these are the formula we use for the calculation of the DC. So these are the full wave rectifier using diode. Now, in case of uncontrolled rectifier, when we are using thyristor, what it is doing, you know, these are the input voltage. Okay, this is the input voltage. Now, in this input voltage, the moment we put the anode positive, immediately it start conducting. But in case of SCR, what we have seen, SCR has an additional one terminal. Anode positive, cathode negative, but still it will not conduct till this gate has some terminal. Okay, suppose I applied this voltage. Okay, so during this half cycle, anode is positive, cathode is negative. If it is a diode, it starts conducting from here. But here, this is applied, it is 0 voltage, but then it become 1, but it is still not conducting. Become 2, this point, still it is not, because gate, I am not given any voltage to the gate. It become 4, I am not giving any voltage, it will not conducting. That means, though voltage across the thyristor is there, but still thyristor or the SCR is not, this SCR is another name is thyristor. Silicon control rectifier, we call another name is thyristor. This thyristor is not conducting. But suppose when the voltage is 1 here, immediately I give a gate voltage. Then what will happen? Immediately it will start conducting from here. That means this part, there is no current flowing through the load during this time. This up to this point, no current. The moment I get the gate, trigger, we call it triggering. The moment you apply voltage on the gate, we call it triggering. The moment I give the gate voltage, immediately it will start conducting. That means, in this case, if you draw the output, how will be the output? Output will be, you see here, first up to this point, no current. The moment it goes to 1 volt, I get the gate triggering, immediately current is flowing. And it will flow up to this point. Okay, then it will be continuing. If it is a full wave, so full wave, what will happen? Second half also it will be coming like this. And I cannot stop it if it is a full wave. So by controlling the gate voltage, I can chop some portion of the waveform. Suppose I triggered the gate at this voltage 4 volt, then what will happen? This input part will not be there. It will be started from here. Okay. On gate is triggered, then you cannot stop. Then it will be conducting. So if we want to control the DC output, I can use the thyristor by chopping this part. That's why it is called, as the starting of the bridge or starting of the rectifier can be controlled by the gate terminal, we call it a controlled rectifier. Okay. These are the control rectifier. Now another important part we will discuss under this video, that is these devices, these power devices, diode and thyristors, it needs some protection. Why it needs a protection? Suppose there is a inductor circuit, the load or inverter which you are connecting. Suppose this is a diode, okay, and I am connecting it through a load. The load has a resistance as well as it has an inductor. It could happen. Load, I don't know how this is the motor load, it DC motor, but DC motor has the inductance. Then what will happen? The moment this switch is closed, it is positive, it is negative, it is conducting. The moment this become negative and this become positive, then the switch is open. Okay. But at that time, what is happening? Just before changing, this diode is a switch, but it's a high speed switch. Just before changing the switch, there is a current. So there is a current I flowing through this. This is a resistor, this is an inductor. The moment this current becomes 0, suppose the current is 10 amperes, suddenly current becomes 0, then what will happen? There is a huge change of current. We know across the inductor there is a voltage developed, V equal L didt. We know this. So within this, suppose 1 microsecond, this 10 ampere current drop, 0 current, it become 10 ampere was flowing, suddenly it becomes 0. So change of current within 10 milliseconds, if 10, then didt very high value and this inductance has a value. So there will be voltage over here. Due to this voltage, what will happen? This voltage, the switch is open. So this voltage, how? Due to this voltage, it needs to flow the current. Current is not able to flow. So this diode will be ruptured or it will be damaged. To avoid this thing, we need some protection to this circuit. That is one. Second way, in case of SCR, the same thing was there. In the case of SCR, if instead of diode if is SCR, due to the reverse voltage, it will also get damaged. So to protect this diode or thyristor from this inductive voltage or due to inductive load, we use some circuit. That circuit but some device. In case of diode, we use a freewheeling diode. We call it a freewheeling diode. What is that? The freewheeling diode across this load. Suppose this is a diode, yeah, and this is our inductive load, okay, and it is coming back to the input, and the diode voltage is developing. So when this LDI due to this, whatever the voltage, this voltage is negative voltage. That means normally voltage positive is negative, but here the voltage is negative, reverse direction as per the law. So this will be positive and this is negative. That means we have to put a diode over here, reverse way. So normal condition, it is reverse bias. When this is a positive, current is flowing through this. The moment this is open, okay, and the inductive voltage in the circuit, the inductive voltage will be drained through this. So the voltage will not subjected to this diode. That means this diode will not be damaged. So this diode we use for the protection of this diode, we call is a freewheeling diode. Okay, freewheeling diode. Similarly, in the case of SCR, we use one RC circuit, that is called snubber circuit. Snubber, SNUBBER. This is we call a snubber circuit. How is that? That is across the diode and cathode we use one RC circuit. Okay. Then suppose this is the inductor, and this is your thyristor. So what is happening here? Also same thing. The moment there is a current stop, there will be voltage develop across this. Then that voltage will be discharged through this circuit, through this RC circuit. So what happens, the thyristor will not get damaged. During normal condition, this is get charged. The moment this voltage becomes zero, immediately it will start discharge, and then this current will flow through this RC circuit, and then the thyristor will not get damaged. That is called RC snubber circuit. So these are the protection device to use for the thyristors and the diode. And in addition to this, we need to discuss another important one point, that is the smoothing capacitor. You know, in the case of half wave and full wave, we have seen how is it. In the case of half wave rectifier, we have seen this voltage profile is like this, right? One of the half is not there. Now this voltage, it is new, this a sudden change. This sudden change we can make slightly smooth. How we do that? We put a capacitor here across the across the load. Suppose this is my lamp or inverter, whatever is there. Okay, here is the input voltage. So what is happening when it is a conducting? So this capacitor gets charged, means this positive half cycle capacitor is getting charged. Then capacitor, what voltage it will be charged? It will be charged at the peak voltage, 4 volt. The capacitor is charged is 4 volt. Then after that, what is happening? After that, input voltage is dropping, 3 volt, 2 volt, 1 volt, 0 volt. When it is a 3 volt, that means here is a 3 volt and here is a 4 volt. So what will happen? This 4 volt will be discharging through the resistor. That means from this point, how much time it will discharge? Till this is not till the voltage up to 0 point, it will, when it is a 4 volt, it is a higher voltage than this. So it will be, this capacitor will be discharging. Okay. Then how much till the capacitor is positive, then this voltage become 2, capacitor will be discharging. This voltage become 1, capacitor will be discharging. This voltage will be 0, capacitor will be discharging. After that, then it is become negative, right? It become negative, but capacitor is 4 volt but is slightly reduced, so capacitor will be reduced. That means in the negative half cycle, when the input voltage is not there, but due to this capacitor, there will be voltage over here. When the voltage will be there, because the capacitor voltage as it is discharging, capacitor voltage will be gradually reducing. Suppose at this point, this voltage become 3.5 and the capacitor voltage become 2. So it will be meeting over here, then this input voltage will be discharging. So it will be during this input voltage passing through this, again capacitor will be getting charged, because at this point capacitor come down to 2.5 volt. Then voltage increasing, capacitor also getting voltage. When it become 4 volt, capacitor is charged fully 4 volt. Then the input voltage reducing, but capacitor is 4 volt. So capacitor will be discharging through this. That means this halfway waveform using this capacitor voltage profile will be like this. So this will be, you see, now this using with the capacitor, if you see the output voltage shape like this. So it is getting smooth. So that's why sometimes we use the smoothing capacitor. But with the smoothing capacitor, problem is there will be lot of harmonics will be there. Though the waveform will be smooth, but lot of harmonics and heating will be there. That's why for high current we cannot use this type of smoothing capacitors. Okay. So to avoid this harmonics and all these things, we use a filter circuit. What is the filter circuit? Across the resistor, across the load, we put on pi filter. Pi filter, you know pi filter, you have learned the pi filter. It is actually two capacitors connected in parallel with a series inductor. That is we call a pi filter. Pi filter looks like this. This is an inductor, and then we have a two capacitor in parallel. This, if I use this pi filter, suppose this is my load, okay, and this is my rectifier here, okay, this is my rectifier. So what will happening over here? So this, during this when the harmonics is passing, this is the output terminal of the rectifier, which is connected to the load, but before the load we have connected this pi filter. So you know the pi filter, how does it work? This pi filter, this capacitor is in parallel, see, right? You know, the capacitor has a impedance or reactance, Xc. Xc equal to how much? Xc, reactance of the capacitor is a 1 by 2 pi Fc, right? 2 pi Fc. F is the supply frequency, C is the capacitance value. So if the capacitance value is high, then Xc will be low. So that means due to this parallel circuit, as the frequency, in the case of harmonics, you know harmonics, what is that? Fundamental frequency multiplied by some factor 2, 3, 4, all are we call harmonics. So if the fundamental frequency 50, so that is going through this. Now in case of harmonics, this F will be 100 to 150, 200, like this harmonics. This is the second harmonic, third harmonics, fourth harmonics. For the higher harmonics, what is happening? This factor will be less. If this will be high means 1 by this means X will be less. This capacitor for 50 Hertz, what will be the reactance? In case of 100 Hertz or 150 Hertz, reactance is very less. So what will happen? All the higher harmonics will be filtered through this. It will go through this and come back. It will not go to the load. So that's why this pi filter, and in the case of high harmonics inductor, what will you in case of inductor, XL equal to, we know 2 pi F into L, it is in series. So in case of high harmonics, inductor will give a high resistance. So in this circuit, what is happening? When suppose it is a 50 Hertz is coming, 150 Hertz is also coming. 50 Hertz, this path for 50 Hertz, what about the impedance over here? What about the reactance over here? For 150 Hertz, it will be 3 times over here and 1/3 over here. So what will happen? 150 Hertz cannot pass through this, it will pass through this. So output will be rejected the harmonics. So that's why by using it is called a pi filter, we can reduce the harmonics. So these are the basic briefs of the rectifier system we discussed. So let's go through this, and then if you have any queries, please come back to us. We can discuss those these comments or your observations. And the next video we'll discuss about the inverter working, how does it work and what are the basic components. So these are the basics of the rectifier system. Okay, thank you very much indeed. We'll carry again in the next video. Thank you.